Hi, thanks for coming to my talk. My name is Oliver Wang. I'm going to talk today about correspondences for video processing. And I'm going to start with a quote from Takeo Kanade. Apparently, he was asked at some point, what are the three most important problems in computer vision? And he said correspondence, correspondence, correspondence. And this is true for lots of computer vision, but I think it's especially true for video processing and video editing. And today I'm going to talk about a few projects in this space. All right, so if you start with a classic image processing problem, denoising, you usually have solutions, for example, non-local means, which basically work by, say you want to denoise a little patch here at the edge of this humming kingfisher, I think it's kingfisher. Then what you do is you find other patches that are similar in the image, maybe around the edge here, and then you average them all together, and that gives you the kind of output color at this location. And you do that for every pixel. So basically, you could think about this as two steps. The first is that you find the correspondences, and the second is that you combine all the observations together. And for non-local means, you find them by some kind of patch matching, nearest neighbors search for patches, and then do a weighted average of these. And and in today's day and age, where we have all of these machine learning-based solutions, I think that these networks that we're training are actually learning to do something very much like this process. And this is because if you train kind of end-to-end a neural network to do a task like denoising, we found that by adding inductive biases, which explicitly find correspondences and then combine them together, we could generally get better results. So these are solutions like kernel prediction, where you predict the weights of a kernel over a region, deformable convolutions, which does something similar, and even self-attention, I argue, is essentially a way to find and combine correspondences. And so for image applications, this works fine, in cases where you have repeated structures, and there are things that you can find in the image that are similar, so you can combine all your observations together. But for video, this is even more true. So if you consider these to be 3 frames of video of a hummingbird here, then if you're trying to find, the nearest neighbor match for a patch here, well, you actually have observed this point on the hummingbird's head at the other moments in time. So, with some local deformation, of course, but there are actual multiple observations of the scene point. And a lot of tasks, boil down to basically having a noisy signal of some kind and trying to figure out how to use repeated observations of that signal in order to denoise it. So, the most typical way you would do this with a series of video frames would be to do something like using optical flow or 2D correspondences. Right? So basically, you would have 3 frames here, compute the flow for a central frame to the neighboring frames, warp these 2 frames so that they now lie over the reference frame, and then somehow merge the outputs together, to the images together to get an output. Um, And this method actually works quite well for many applications. So we shipped a deblurring application that did this, where the merging step basically took the highest frequencies in a Fourier transform over the image stack. And this was shipped in After Effects to do camera shake deblur. It's kind of deblur after you have stabilized a video. And there's been lots of papers also that have used such methods for denoising as well. So this is an example of an end-to-end system where these steps of warping based on optical flow and combining together is trained end-to-end to do video denoising. But I'm not going to talk today about 2D correspondences. I'm going to talk more about 3D correspondences, which is an area that I think is particularly exciting right now. And I'm going to start with a paper which is actually a very old paper. So this is 2015, which is before the deep learning era, at least for me. And this was published in a graphics conference. So perhaps this is new to you here. But the idea behind this work is that we wanted to try to do video processing by thinking about points in a 3D space rather than thinking about pixels in 2D. And the reason you work in 2D typically is because it's very efficient. So you can search for patches, the data is all there, local in memory, and is robust. You don't need to have any 3D information, so it works all the time. But there are reasons why you'd rather work in 3D if you could. So the world is 3D, and of course the video is just a projection of this 3D world. So if you're averaging patches together, it makes a lot more sense to do this patch averaging in 3D. So you don't have to deal with this projection operation, which gives you like depth discontinuities and things that end up being really tricky when you do 2D correspondence averaging. In addition, what's really important is that working in 3D, it kind of abstracts the camera or the viewer from the equation. So this is for this project, we're going to assume that we have a static scene, but later on in the talk, I'll go into methods that relax that assumption. But yeah, so assuming your scene is static, then you basically, by working in 3D, you're guaranteed to get temporal stability of your results back out again, which is really nice. Okay, so this method has 3 steps. The first is projection, where we take all the pixels and throw them in 3D. Next is sampling, where we figure out which of these samples we want to gather for the final step, which is the filtering, where we produce the output color, which is application specific. And in this paper, we basically showed that we could do a bunch of different applications under this exact same framework by very slightly modifying this filtering step, the third filtering step. So we could do things like typical video processing, like denoising, deblurring, super resolution, but then also some sort of higher level enhancements like virtual apertures, in painting and action shots, for example. All right, so going into how this works, we'll start with the projection step and basically taking a video. So assume this is an input video of a scene. We run basically off-the-shelf camera pose estimation using SLAM or structure for motion, and then get dense depth values using multi-view stereo. So here you can see that the depth is pretty dense. It's not entirely dense. We still have some holes in places we couldn't find reliable correspondences for the multi-view stereo step. But then we can take these camera poses and these depth maps, and we can basically project these frames into 3D. And the kind of interesting thing here is that this is a visualization of just 5 frames of video, and you can see kind of how crowded this point cloud is. And there's so much data in video that, like, if you just take, for example, 30 seconds of 1080p video, you're already dealing with 2 billion pixels in 3D, which is a huge amount of data. The data is noisy because the depth estimates are incorrect, but you have so much redundancy that we found we can get good results just by tuning the way that we combine all the noisy samples together. Right, so the next step is sampling, and this is basically for a given output camera view that you want to render. You take a pixel, and we treat this pixel as a box. So basically, there is an area to it, and then you can project this frustum into 3D, and you can gather all of the samples that exist within this frustum, which you see here. And these samples have a number of features to them. There's, of course, the color from the view that projected into that space. There's the position in 3D. There's the time in the video that it was recorded. And there's also the size, which kind of has to do with how close this point was to the camera. Because if the camera is really far away, then the frustum is really wide by the time you get there. And so we're going to take that sample set, and then we're going to filter this and get a single output color to put into this output frame. And this is the filtering step, which is the application-specific part. And basically, we're going to phrase all of these applications that we do just as a weighted sum. So basically, we have a weight, and this weight, which I'll describe how to derive this weight, but you just weight all these samples and sum them together. So now let's go over a couple applications we can do with this framework. So the first, for denoising, we have this video here, which has both spatial noise and also some temporal noise due to some aliasing of these lights and the camera. And we come up with a weighting scheme, which is based on a bilateral filter, which basically weights each pixel based on how similar it is to the reference pixel in the output view, which is kind of like a more reliable observation. And by doing this, we're able to get a denoised result that looks like this. I don't exactly know how well this is coming over video, but I'll try to put these videos online somewhere so that you can see the quality without compression. But we compared to state of the art, and we found that it worked better. This was, of course, 2015, so I'm sure the state of the art is better now than it was then. We can do deblurring, so this is a common deblurring data set, and we can basically just weight each sample by how blurry that frame was. So we have a measure of blurriness for the entire frame, and we downweight samples that come from blurry frames. And basically what you end up getting then is a video that is reconstructed out of just the sharp frames. So you can see this text becomes legible here. We also compared this to state of the art, and it worked pretty well relative to that. Okay, the next one is super resolution. In this case, we have a weight for each sample based on the size of that sample in the pixels frustum. So basically, this will weight samples that are observed from closer, so therefore have like a higher spatial resolution. Of course, this only works if you actually observe that sample closer, so it's not like a general purpose super resolution solution. In painting, as actually has a very simple weighting function. So in this case, we require an additional 2D mask that identifies the region to remove. And then we come up with a weighting function which just basically zeroes out the contribution of samples from inside that mask. So they can't contribute to the final color, and what you get is just the things that were behind it. So it's just based on the mask. We can also do computational shutter effects, which I think is kind of cool. So an example of that is shallow depth of field. So we can simulate a lens rather than a pinhole camera model. We basically do this by changing the sampling volume. So we will now increase the sample size as if the frustum for that pixel came from a lens. So we have like a focal plane, and then it diverges after this. We kind of use a double cone model. And then we can simply average together these the samples inside this aperture, and we end up getting a result like this. And you can see in the shallow depth of field version that you have kind of nice behavior around the discontinuities, which can be a little tricky. And then finally, in this example, which has a connect up here, which it means that we used a depth sensor so that we could handle scene dynamics. We show that we can do kind of action shots by a comb filter on the weights of the sample. So basically, we just keep samples from 1 out of every n frames, and then we get this kind of neat effect. And at the time we did this, there was a few depth sensors, but they were a little bit tricky to work with. But now phones have depth sensors on them, most phones, modern phones. So I think there's some neat computational photography applications using that. So in conclusion, these 3D correspondences are good because they don't suffer from drift. They kind of handle these long-term correspondences across time nicely because the viewer has been abstracted. But there are some disadvantages. They're computationally expensive. They're not very robust because you need to be able to reconstruct the scene in 3D, which you can't do for all scenes. And then you can only work this on static scenes, really, except for the last example. So I'm going to shift gears a little bit now and talk about handling scene dynamics. But to start, I want to get into kind of this new area that came around with this NERSC paper, which I don't know if everyone's seen this, but it's a way to do view synthesis based on a set of observations. And this paper has these amazing, beautiful results. It's really cool. It just inspired a ton of follow-up work. But the idea behind NERSC is basically that you approximate the radiance of a scene. So you reconstruct kind of a volumetric representation of the scene by storing that volumetric representation inside of an MLP. So at each location, so we have an XYZ here, and then at each viewing direction, which is this theta phi, we basically store the RGB and some kind of transparency value. And then you can use standard volume tracing to render the results of this representation, and then you can sort of train it. Sorry, you can train it to match the color of the image here. So when I volume trace this ray, I need it to match this image, and this kind of optimizes the whole representation. And I kind of would argue that what this is doing is kind of taking these observations you have from all of your images, and you can sort of visualize this as you're shooting rays into your space, and you're requiring that your 3D representation along these rays matches the observation. And then you have a bunch of different rays you shoot from your entire image collection or video. And you kind of rely on the smoothness inherent in this MLP in order to average the results together, to kind of aggregate everything. So there is a baked-in smoothness prior in that this MLP cannot represent kind of arbitrarily high frequencies. And that smoothness prior is really important for getting nice interpolation results in the end. But how does this go into dynamics in video? Well, the next project I'll talk about was for CVPR this year. And this is a project done in collaboration with Cornell and Adobe Research. And it's called Neural Scene Flow Fields for Space-Time View Synthesis. And the idea here was that we wanted to be able to take a single input video of complex dynamic scenes, such as this one here, of my son, with bubbles and some large motion and kind of tricky scene, not a lot of camera motion either. And we wanted to be able to synthesize both novel views in space and in time. So we take this input and be able to generate output like this. In this case, this is a fixed time and the view's moving. This example in the middle is, 1 second, sorry. Yeah, so this example here is fixed view and the time is interpolating. And this example here is both interpolation in space and time. Okay, so in order to do this, we need to be able to find correspondences in the moving object across frames. So if we just use the default nerf out of the box, we end up getting this. And this is kind of expected because this nerf has no notion of time, so it has to kind of hide the dynamics in the view direction. So you can think that we just add time. We condition this MLP on time as well. And let's just try to reconstruct this scene. And if we do this, we find that it actually did not work very well. This is because the MLP was not kind of tying together the different frames in time in a way that made sense. It gave it too much flexibility in what it could represent. So we're going to constrain the representation by requiring that it finds the scene flow, which is the correspondence field from one frame to the next, at every position, view, direction, and time. And the scene flow field, kind of interestingly, I think, is that it's going to be represented dense and continuously in our entire 3D volume. So we're not representing the scene flow in image space, but we're doing it in scene space. And this is nice because we don't need to be able to handle discontinuities that happen at scene flow boundaries. So we can kind of have this smoother representation of scene flow, and it still represent the motion of the scene. So in order to train this, we need a loss function that constrains the scene flow. So the way this works is that we have a bunch of scene flow vectors, and we're going to warp the neighboring time into the reference time, and we're going to basically restrict the reconstruction along this warped ray to equal our reference view. So in order to do that, we cast a ray through our reference view from the camera from our reference view, and then at each point we look up the location based on the scene flow to get the colors from the neighboring time. We paste those back along the ray, and then we volume trace this ray and get a result. And then we say that this should be like the observed color of the reference time, and we have a loss on this. Right, so basically what this is saying is that the reference image should be consistent with the scene at the neighboring times after you have undone the motion that is due to the camera motion and scene flow. So this is only correct if you can undo the camera motion and scene flow. Okay, what if we do this? Then we end up getting a result that is wrong most of the time. This is because there is inherent ambiguity in that you can describe the same observations either with camera motion or with scene flow, right? So your object could be really close to the camera and moving slowly, or it could be far from the camera and moving fast, and it would look the same. So how are we going to fix this? We're going to introduce a couple of data-driven priors. Specifically, we have two main priors that we use only for bootstrapping, for initialization, because these priors themselves have errors. But it's nice to just get you in the neighborhood of the correct solution, and then you let the optimization go. And these priors we use are a single view depth prior, which kind of gives a relative depth of objects in the scene. And then we constrain that the projected scene flow should look like the optical flow. And that these two things together kind of help put you in a nice location to start your optimization, which puts you into a good minimum. So we want to do both view and time synthesis. And the question is, how should you render this time synthesis? So what you could do is you could just evaluate the scene at fractional time values, like t equals 0.5. But if you do this, you get the result on the left, which doesn't look great. But because we are explicitly solving for the scene flow, we can actually render in between times by evaluating the colors at discrete times and then warping these by the scene flow into the intermediate times. And this gives us the result on the right, which is which is correct. And actually, this is, I think, a good way to visualize that the scene flow is right, because if the scene flow is wrong here, then it would give us the wrong interpolations. Okay, so that's how the method works. Let's look at some results. Um, all of these examples are computed from a single video shown on the bottom right. And you can see that these are pretty challenging cases. We have thin objects and lots of motion. We don't have a lot of input frames, but the method still is pretty robust at reconstructing these dynamic scenes. Yeah, it works also with occlusions here. And there's some nice view-dependent effects on the wood here. Yeah, also in this case, the floor has some view-dependent effects. Okay, cool. We did some comparisons related work. These comparisons are all are old because there's a bunch of related work that came out since our paper. But we found that it was more robust than the existing solutions. And then there's another application you kind of get for free, which is 3D video stabilization, which I think is kind of cool because you can stabilize this video without having to crop, because you're re-rendering the entire scene with a smooth 3D camera trajectory. Yeah, so that's it. So the takeaway message, well, I think it actually worked quite well. The depth and the scene flow seem correct, so we get these really nice depth maps of dynamic scenes, which is cool. We also visualize the scene flow, and we have these nice dense scene flow fields. So I think there's a lot of stuff you could do with the scene flow that we haven't even looked into yet. Um, what are the bad things? Well, the bad things are that we only were able to get it working on small videos with not a lot of frames, and it takes a really long time to do the optimization, like 2 days, for example. It also requires the camera pose beforehand, and then kind of more conceptually, I think it's really limited in that you're basically just able to do view synthesis. And I know that there's a lot of papers on view synthesis, but I feel like view synthesis is a little bit of a boring topic. It's people show it because it's kind of easy. We can generate results because we can train based on held out views, which is nice. But this workshop is about image manipulation, so we'd like to do more than just view synthesis. So how do we use these kinds of correspondences to do video editing, actually more creative tasks? And that's the next paper, the next project I'm going to talk about. And I'm going to go back into the 2D domain here. And the reason why is actually because I think that humans kind of interact with the world in 2D. And this is not something that is new or from computers, but kind of like since the beginning of time, the origins of art are these kinds of projections of the 3D worlds onto a 2D plane. So humans very naturally interact with 2D display devices and input devices. So the question we wanted to answer was, how do you edit multiple observations of a world, say a video, in 2D in an easy way? So we need to parameterize this world onto a 2D manifold that we do the editing on. And this is a project called Layered Neural Atlases for Consistent Video Editing. It will be presented at SIGGRAPH Asia this year. And this is a collaboration between the Weizmann Institute of Science and Adobe Research. And the goal here is to do consistent editing of videos across time. So it's kind of hard to edit an entire video at once because you can't draw on all the frames. So we want to take this video and we want to generate something like this. So we've added flowers on the dress, and we've added some colors onto the bench, and we want them to interact correctly with the shadows and also track with the objects and the camera as it moves. So this method is based on the concept of these layered 2D atlases, right? So we're going to have the input video, and then we're going to estimate atlases, which are a parameterization of the world over time onto a single image. And we're also going to estimate the correspondences from every pixel in the input video into a location on this atlas, on the set of atlases. So then we can edit the atlases and then map these back to the video to render the resulting video out. Okay, so how does this method work? So we're going to use these coordinate-based MLPs again, and we're going to use the machine learning toolkits to do the optimization, similar to the previous paper. So we have our input video, and then for every XY time, every location in this video, we're going to have two mapping MLPs, which are basically going from that location in the input video into a location in each atlas. And then we're also going to have the atlases themselves represented as coordinate-based MLPs. So this atlas takes a 2D coordinate and produces an RGB color. This is an example of what these atlases look like. And then we're going to have a alpha transparency MLP, which predicts a blending value, which we can then use to composite the colors from the atlases into a final output color. So we could basically reconstruct the entire video just using the colors in the atlas by using the correspondences and this blending weight, this alpha blending weight. And therefore, we can train this entire thing end to end with a reconstruction loss. Okay. Actually, we have a number of losses, and I'll go over what these are. So the first one is this color loss, which is a reconstruction loss that I said, that the reconstructed video through the atlases should look like the input video. And then we also have some other losses to make the atlases more intuitive to a human. So we want to try to reduce the deformation in this atlas. And we do this by saying that triangles in the input video should remain similar to triangles in the atlases. And you can see that without this rigid term, we end up getting these atlases, which can do a really good job to reconstruct the video, but they're kind of highly distorted. So it would be tricky to go in and draw on these atlases. We also want to constrain that 2 points that are connected by optical flow should map to the same location in the atlas. And we can see that without this, actually kind of interesting enough, without this, it does still work. So the network is able to find some correspondences, but it occasionally misses things. And you end up getting, for example, duplication on the motorcycle here, and just a little bit worse reconstruction in general. And then the last loss is that we want to encourage the minimal atlas. And the reason why we do that is because a perfectly valid atlas could actually have every single frame contained inside of it. And then the mapping network could just have to look up the right location in this 2D atlas for each frame. But this is obviously not very useful because we wouldn't be able to then propagate edits the right way. So here you can see that without the sparsity loss, you end up with 2 motorcycles. But when you have the sparsity loss, you end up with what you would want, which is a single representation of the foreground and background. So let's see some results. So in this case, in this video, we took the background and ran it through a kind of off-the-shelf image style transfer method. And you end up with this video where the background has been stylized by the style transfer. In the next example, we take the background atlas and actually just replace it entirely with another image. And then this renders this ship going through a very different environment. Yeah, so that's that. So the wrap up for the whole talk, I think, what are the take-home messages? That I think video editing, video processing can be viewed of as a correspondence problem. We basically need to find all of the observations of the same scene point and perform the same edit on that scene point. So there's a lot of different ways we can do this kind of correspondence. We can find correspondences in 2D. We could do it in 3D. We can do it implicitly through using an MLP representation. And then there's probably other ways to do this that we haven't come up with yet. But we should think about this general problem setting, and I think it will enable us to do cooler things with video editing in the future. The other thing I want to say is that this kind of end-to-end training is really good for view synthesis, but we haven't quite figured out how to do it for other editing applications yet. It's not as easy to get the held out training data as it is for view synthesis. So we need to come up with other ways to get kind of before and after editing operation data so we can train networks end to end to do those editing operations. So yeah, thanks for coming to my talk. So I have to just plug at the end. We are currently looking for interns, student collaborators at Adobe Research. So please feel free to reach out if you want to work in this domain or are interested in Adobe in general. I'd be happy to talk to you. Thanks.